Today's topic is Green's theorem. This, in the fundamental theorem of calculus series, this is the third one, 3.0. I named it 3.0. And mathematician slash physicist Green, and is a big deal in applied maths again and physics. He came up with this. Okay. So, but let's review a couple of 1.0 and 2.0 of the fundamental theorem first. Okay. So 1.0 is like this. Say you have a function, looks like this. This is f versus x, and then you take an integral, right, from a to b. So this integral from a to b of f of x dx, right, which gives you area of this. But amazingly enough, this thing is f of b minus f of a, right? Antiderivative, where df of dx, and this is like, maybe you don't like this, like this is commonly used, that function of x is equal to f of x, right? So if the antiderivative exists, derivative antiderivative relationship, right? This is a derivative, this is antiderivative, but we can think of this as also as a boundary idea. See, I'm gonna put this little, I'm gonna put it in right here, different color. See, that didn't work. Hold on, not that one. This, oh yeah. Okay, let's look at that interval, a and b. Right, so we are thinking of this as an interior. And when I say interior, I mean this, right? And the a and point B, these two are boundary of that region that we are integrating over. You know what I'm saying? You kind of understand what I mean by interior versus boundary? This thingy plus the boundary gives you our a to b close interval. You know what I'm saying? So our close interval a to b is equal to, how do I want to say it? Oh yeah, like this. Interior union you know what I'm saying? That's a very big deal. It's distinguishing. I mean, we kind of overlooked it last year, but now when we talk about Green's theorem, this is a big, big, big deal, okay? Let's talk about 2.0. 2.0 looked like this. You have some kind of a space curve given by C, right? And there's some kind of a vector field. Right? So the integral along C of your vector field f, and which could be function of x, y, and z, by the way, right? Dot dr, and r of t is what describes that curve C. You know what I'm saying? R is a vector function. This thingy amazingly turns out to be f of whatever x, y, z, but starting at point, this is the point where t is equal to a, and this is the point where t is equal to b, right? So a, b, let me just put it like that, b minus f of a. You know what I'm saying? X, y, z, but just to abbreviate. So now what was the relationship between the two? This is a scalar potential function, so this should be a derivative of f, right? What do you mean by derivative? Derivative with respect to what did we do? Oh, come on. Which variable are we differentiating this by? Remember, this is multivariable calculus.
The position.
All of it, right? Space. That is equal to f. You know what I'm saying? Gradient, right? Take a derivative with respect to x and attach I, that thingy with respect to y and attach j, and that thingy with respect to z and attach k. So that that potential function becomes a vector field. You get it? But let's just think about this. This vector c, I mean the curve c, we can look at this as an interior. You know what I'm saying? And these two as a boundary. You know what I'm saying? So nevertheless, we can look at this as interior and this as a boundary. And that's a boundary as well. Endpoints. So far, so good. So far, so good. Okay, because I'm about to state the Green's theorem, and this is gonna blow your mind. Now we're back with, oh, this thing is getting bigger. Fundamental theorem of calculus 3.0, which is Green's theorem. Of course, if I can learn to spell green. Okay. Now I'm gonna draw the picture for you. Say there is 3D coordinate, 2D coordinate. This Green's theorem. So far, I can have a 3D version of it, but let's just stick, because 3D version in this book is also called the Stokes theorem. It's like technically same thing, but not really. Say we have that kind of region. What? Okay, so if we have a parametric curve, I'm gonna make this thing black. And we can still have some kind of C. You know what I'm saying? In conventionally counterclockwise direction. And we have that region D inside. Okay, now we have to distinguish the two. D here is interior. And C here is boundary. Why can't I spell today? You know what I'm saying? So when we say D, D is the open interval kind of idea, which is known as the open region. It does not include the boundary. You know what I'm saying? And then C is the boundary, kind of acting like an endpoint. So this, just like both of these, because the fundamental theorems, this is the boundary. This is the interior. You know what I'm saying? Interior, boundary. This, once again, is a boundary on this side, right? This is the boundary, and this is the interior. You know what I'm saying? So now we are looking at, we have boundary that is some kind of closed curve, because we can have a parametric curve like ellipse, circle, otherwise, that encloses the whole thing. And then we have an interior. So far, so good. Now, this is what Green's theorem states. If you have double integral in that interior region, and then what we were going to have is this thingy cross product with a vector field. What? and you haven't even learned this thing yet. It's known as the curl. And you dot that with dA. dA is our usual dx dy, but I want to give a direction for dA vector. Ooh, scary. Don't be scared. That is just a k vector standing up, pointing out of the page at the moment, okay, by convention. Because your book has a stupid notation, but I'm gonna lead you. This is like setting you up for Stokes theorem in 3D version. So it's like I'm gonna use exactly same. Is equal to, remember that symbol? Over your boundary, the curve, around, line integral going around in a loop of antiderivative of, what's the antiderivative of that thing? This already looks like a derivative because that thing has a partial x, partial y, partial z in it. You know what I'm saying? So antiderivative of that thing is just f dot dr. Remember that this is r vector function of t. Why did I put it there? Bring it. That's what describes this curve C. You know what I'm saying? This is a content of Green's theorem. Right? Okay, shall I break it down for you then? Yeah, okay. Suppose F has a x and y in it at the moment, right? And this is a vector field itself, so think tornado. So you have P, x and y, I vector, plus Q, x and y, j vector, right? You remember when you're doing tornado, you have to do x component, y component, and z component. So this is minus the z component. Z component is 0. Let's just think like that. So this is two-dimensional vector field. Good. Let's take a cross product of this thing with F and let's see what that thing even like. What does it even look like? Okay, so cross product is done with I, J, K, and then this is partial with respect to X, partial with respect to Y, and partial with respect to K, with Z, right? Your gradient thingy, but it's still not, this is not gradient because you're actually crossing it with a vector field. Because your gradient was this thingy to a scalar function, your potential function. Now we are actually crossing it with a vector field. And this thing has P, Q, and 0. You with me? Say yes. Okay, this thing will turn out to be then, let's say, I vector this, which is 0, minus this. See, this has a z. This is a derivative with respect to z, but q only has x and y in it. So this is 0 as well, right? So that term is 0. J, this minus this. See, z once again, this is 0, and then you multiply with 0, 0. So that's 0. Only thing that survived is this k. So this way, so you have partial q over partial x, right? And then minus the other way, so partial p minus partial y. You with me? And times the k vector. That's what the curl of F, del cross F, looks like. Okay. And then, of course, your dA. Oh my God, this computer is just doing. And of course, your dA is, I'm going to write it here. dA vector just means your dA dx dy times the k vector. Okay, so upward vector. So we can, just because we can take a dot product. Okay. Let me rewrite that Green's theorem now into the textbook version. So your textbook version of Green's theorem looks like this. D of that cross product, which we computed here. So I'm going to put that thingy in. Partial Q, partial X minus partial P, partial Y, right? And then K vector dotted with that dA vector. So K just disappears and gives you dA. You know what I'm saying? And the other side is really annoying in your book. They just put this P dx plus Q dy. And they don't even put parentheses, but that's really, what does that mean? That looks really weird now, doesn't it? It does not mean they are single integral with the x and y. No, this is still line integral. So this is really our usual f dot dA, okay? You have to find the vector function r and take a derivative and then dot it with your f function. You know what I'm saying? But they just write it like this for some annoying reason. That's why you see my motivation of giving it to you in this 3D Stokes theorem version. Because how are you going to remember this? Remembering this itself is not an easy thing to do, right? But just think cross product. See, this is easier to remember because remember, fundamental theorem, this side is antiderivative and that side is derivative, right? Derivative, interior versus antiderivative, the boundary. You get it? So it's just exactly the same theme. Interior versus boundary. Interior is the derivative of something, right? And the boundary is the antiderivative, that thing. This is that relationship. Okay, so are we ready to prove this? And then I'm going to write this just to make sure that dx dy is not really like r, vector function r of t here is your x, function of t, I vector, plus your y, function of t, j vector, our vector functions. So dr will be dx I vector plus dy j vector, okay? So this dx dy really means this thingy, okay? Otherwise, it's like really confusing. I never like that notation. That is dumb. You should put dt outside. I mean, if you will. You want me to just put dt here? So that you know it's really over. Oh, no, I shouldn't because this over dt times dt is really what they mean. So it's like, let's not, but you kind of know it's there. Shall we prove it? Yes, we shall. Okay. Now, this thingy, I'm gonna break it down, okay? This thing has a statement 1 and 2. I'm gonna put it right here, statement 1. Here's a d, q partial x, okay? And then dA, dx dy. Actually, I'm gonna spell it out. Dx dy dx. Okay, is equal to that the just with a p. And then statement 2. Oh, whoa, I screwed up. This thing is q. Q dy, right? See, I'm taking q separately and p separately. And then statement 2 will have this negative partial p partial y now, right? dy dx is same as, well, this is over d, and this is over c, the boundary, and then whichever has p in it, p dx. Okay. So far so good. So do you agree that if you add these two integrals vertically, then we get exactly this? Now, if that is true, does not mean this is true. Converse is not true. But if both of these are true and we add the integral, then that's definitely true. And that's all we need, because we are only going to prove these two separately and add it and get that thing. Is our tactic. Do you see the tactic so far? Okay, now, then I'm just going to prove this thingy today. And I suggest you prove that statement at home. Okay? Okay, so let's prove it. Proof of statement 2. Okay. Now, I'm going to start with that thingy. So negative double integral over d partial p over partial y, and then dy, and then dx is what I'm starting with. Good. And I'm going to recycle this picture. So hold on, let me go copy that picture. Hopefully it copied nicely. Okay, it copied nicely. Okay, I have that thingy. Okay, I'm going to try to evaluate this thing. So negative double integral. Ooh, how do we evaluate this thingy? Well, I'm going to erase this C now. Should we go in that direction? So function to a function and boundary A, let's say this is boundary B. So I'm going to call this thingy y is equal to some g, some function g, and this is y is equal to some function h. How about that? This is y1 and this is y2, if you will. Are you with me? Then this double integral, I can say, outside is from a to b, and inside is from h of x to g of x. Correct? And then this thingy is the derivative with respect to x of your function p, which has two variables x and y in it. Are you with me? That's how we used to evaluate the double integral all this time. Say yes. Okay, now we'll actually evaluate it. What? We don't even know what that function is. How can you evaluate something when you don't know? Watch this. This is already a derivative with respect to x, isn't it? You know what I'm saying? So integral of that is just a derivative. Oh, I miscopied the problem. This, remember, this is partial y, and I just changed it to partial x. So I'm gonna go back and change that to partial y, okay? So if I'm integrating with respect to x, and that's already a derivative with respect to y, and integrate with respect to y, I just cancel that thing. Good. So what I have here is just get the p back. Our function x and y, right? And then y starting from h of x to g of x. And then we still have dx to do, correct? Do you agree with that statement? Now we substitute. So we have a to b, Now this is y is equal to this, so we substitute this variable minus that variable, correct? So what we are going to have is p, and then we have x and g of x. So when you make this substitution, your y disappears. Remember that? Minus your p function x, and then you substitute h of x. And dx. Still with me? If you're confused, now is a really, really, really good time. You with me? Okay. Now I'm going to break this integral into two different pieces. So I have negative of a to b of p x comma g of x dx, and then this thing is plus now, negative integral of a to b p of x comma h of x dx. Still with me? Okay. Remember negative sign a to b, so I can use plumbing professor and make that b to a. P, x, and g of x dx plus from a to b, p of x, h of x. Still with me? Time to zoom out and look at the big picture, okay? Now, this is misleading because it looks like a single variable calculus, but this is still multivariable. This is parametric function, dx over dt with a dt, right? So if you look at this from b to a, g of x, right? That's b to a is along this line integral, isn't it? And this thingy, a to b, along h of x. So that's from here, this line integral. If you put it together, then you get this entire line integral in closed surface. Good? So this thing gives you this line integral over c of your p. And then this is x and this is y, different y path. So it's like xy. And then dx. How about that? What have we done? What we have done is go back. We have proven this statement. Likewise, you can prove that statement, and I strongly suggest you do it, that you want to integrate that way. So sideway, call this c and d, and then reverse the order, dx and dy. And then you can easily prove this the same way. Then you add these two together, then you get that entire expression, which is called Green's theorem. Dang on. Wow, right? Shall we take an example to make this thing concrete now? Yeah, let's do that. Okay, let's go back down here and take an example. Let's say we want to find area of ellipse, x squared over a squared plus y squared over b squared is equal to 1. Of course, we know the answer is pi ab by now, right? But just to illustrate the power of this, so I'm going to throw this ellipse like that, and then throw the coordinate axis. This thing always never centers it itself. I don't know why. Never. Okay, like that. So this is A and this is B. Negative A and negative B. Okay, we want to find the area of this. Okay, and of course this is the here's a nice gimmickry, okay? If I just write that thing, this thing with the respect to x minus partial p, partial y, right? That thingy, with dy over dx, okay? That's ugly. And then call it a d, and d is this thing, d. I want this thing to be 1 dy over dx, d. Like, why would I want 1? Because then that's the exactly area of this ellipse now, isn't it? Okay, 1, I don't even know the vector field. We can come up with it. Watch this. So what I want here is this thingy minus this thingy. I want this to be 1, right? I mean, we can choose these things cleverly. Now let's see, q is equal to, and this is like example in the book, and then p is equal to -1/2 y. Let's see. So if you take a derivative of this thingy with respect to y, you get negative, negative, +1/2. If you take a derivative of this thingy with respect to x, then you get 1/2. 1/2 plus 1/2 is 1. Oh, that's true now, isn't it?
I think you accidentally wrote dq over dx.
What was that?
I think you accidentally wrote dp over dx instead of dq over dx.
Oh my God, that no longer some of you look confused, right? Because dq over dx, right? So this with respect to x, you get 1/2. This with respect to y, minus, you get +1/2, which is equal to 1. So first August, so you see why this becomes 1. Okay, then we convert this, wrong color. We convert this using the Green's theorem, right? And then p dx plus q dy, which is the contents of our Green's theorem, okay? Now, let's write this vector function, shall we? This vector function is a cosine t plus b sine t, correct? Oh, I forgot the vector symbol, ij. Here's I and here's j. Good. Say yes. Then my dr, in order to differentiate this, I'm going to have negative a sine t I vector plus b cosine tj vector times the ta. I'm going to push that to the side a little bit because it's going to overlap with my integral. Okay. So let's actually integrate it, shall we? Okay, so what we have here is integral of p. P was 1/2 x, correct? Correct? P is -1/2 y, and -1/2 y happens to be here. This is y, isn't it? Let's review. This is x of t, and this is y of t. This is how we do line integral, right? So y is -1/2, and then b sine t. Good. Dotted with dx, which is this thingy. So -a sine t. You with me? This is a dot product, right there, plus, and then your q is 1/2 x. So that's 1/2, and x is this thingy, a cosine t. And times dy is this thingy, b cosine t. With me? dt. So even if it looks like a single variable calculus, it's still line integral. You do it our usual f dot dr way. Still with me? Okay, let's see what we got. So this is from now 0 to 2 pi because we have dt out here. Okay, we have ab sine squared, right? And we have ab cosine square. So we just have half of AB, correct? dt from 0 to 2 pi. What does that give us? It just gives you t, 0 to 2 pi. So this thing gives you 2ab. I mean, 2ab, pi ab. Today's example, we have to perform that. Although this is written like that, it still means the line integral here, here, here in that direction, right? Unless otherwise mentioned, line integral around the closed loop is always the counterclockwise positive direction, okay? Now, I was saying this is pain in the butt. Why is this pain in the butt? This line integral. Oh, come on. Because you need 3 different vector functions, right? One for this, one for that, and one for this, right? Then we have to do this, break it up into 3 different integrals. You see how long that can get? So that is why this is pain in the butt. Okay. Then idea is, could we use Green's theorem? Right? Okay. What is Green's theorem then? Do you remember content of Green's theorem? Let's quickly look at the Green's theorem. Okay, Green's theorem is this, right? You have to take a curl of this cross product of this thing, PQ. So mainly Q and P. You know what I'm saying? Derivative with respect to Q and derivative with respect to P. And then we'll do this one more time. You know what I'm saying? Okay. So, and then we can convert it into double integral. You want me to copy this thing? I think I should copy this thing, right? Okay, I'm gonna copy this content. Did it copy? Copy. And then I'm gonna go back to today's note. Okay, we're back here, and then I'm gonna paste it here. I guess not there, paste it here. Okay, we are going to use this Green's theorem. All right? Okay. So which is P and which is Q then? Do you see that this is P right there and this is Q right there, correct? Do you see that? Okay, so we have to take a partial derivative. So we'll start right here. We'll start from this side, and I want to use blue. We'll start from this side, C, and then x to the 4th power dx plus xy dy, that thingy. Now, remember once again, this is P and this is Q, okay? And according to this theorem, now we can convert this into double integral over that region D, and we are going to I made integral two times. Actually, yeah, that's okay. This region of partial derivative of q with respect to x. Would that be y? Good. And partial derivative of p with respect to y. Well, that would be 0 now, wouldn't it? dA. This has turned into a trade-off. Right? Line integral is generally pain in the butt. This is a double integral, but this is not a bad trade-off. And our thingy, by taking this derivative, curl, it got much simpler, didn't it? Okay, and then we just evaluate the double integral. Should we go in this direction like that? Yes, we shall. So your x will vary from 0 to 1, and your y will vary from 0 to 1 minus x, eh? And then you have y, and then we'll evaluate y first, then x second. With me? 0 to 1, and this is y squared over 2. Evaluated at from 0 to 1 minus x and dx. Good. Okay. I'm going to take out 1/2 to the outside. And then I'm going to substitute and square u. It's not that bad. Suck it up and do it. So we have 1 minus 2x plus x squared. Say yes. Are you getting lost? And that will be 1/2 of, so we have x minus x squared plus 1/3 of x cubed from 0 to 1. Good. And this is the most challenging part. So if I do it in my head, 1/6. How about that? You see how Green's theorem can be useful in evaluating line integral. Any questions before I move on to the next example? Okay, we'll look at this example then. Wow, that's humongous. Wait, let me resize this a little bit. Okay. So our path is this. That's our path. You see it's going to be terrible, right? So I'm going to call this thingy C1 here, and this is C2, and that's C3, and this is C4. Okay? I mean, this example really wants you to use Green's theorem to do this, but I think it's a very good practice to just do the line integral anyway, because I feel that you're not doing enough homework and you're getting behind in line integral. So we'll actually do this thing both ways. Okay, and we'll compare the answers and see which one is easier. Of course, double integral will turn out to be easier, but we'll still do it anyway. Okay? Okay, so since I hate this thing, this is p and this is q, so let me rewrite this as a vector function. So vector function of x and y will be this thingy here. So it's y squared I vector plus this thingy here, 3xy j vector is our vector function, because we have to do line integral, so it's much more convenient this way. Okay? Okay, then we'll do C1. C1 path, this path right here. Okay, let's come up with, oh, did I say vector function? I meant vector field. This is a vector function. Okay, we need the semicircular path. So should we have radius, and then cosine and sine will do? Cosine t, I vector, plus 2 sine t j vector. How's that? Okay, and our t will vary from 0 to pi. That will give you a semicircular path, correct? Say something. say an indicator that this doesn't sound like Greek to you? Okay, that nod helps a lot in teaching, trust me. Now, we have to do f dot dr, right? So we'll calculate dr. That's ugly, d. Let me zoom in a little bit. So dr, okay, we take a derivative of this thingy, so we have negative 2 sine t I vector plus 2 cosine t j vector and dt. Are we good? That's what they mean by this thingy, right? They don't mean just x and y. No, this is y, and how can you, right? They literally mean f dot dr of this thing. I mean, that I really, really hate that notation, okay? So now we have to convert this f function according to these two, right? This is your x and this is your y, isn't it? Yeah, so let me show you what that looks like. So your f back here, go back to red. Your f now will turn into this. So I'm gonna, instead of x, but I'm substituting that function t, you know what I'm saying? Y sub t. So that will be y squared, this is y, you get it? So we have 2 sine t squared I vector. Are you with me? And then second one is 3xy. So we need plus 3. X is this and y is that. You get it? Okay. So we'll do. No. X is this and y is that. I pointed to dr. That's the xy. So we have 2 cosine t and 2 sine t. Oops. 2 sine t j vector. Do you know how to do f dot dr now, right? And we are going to dot this thingy with that thingy and shove it inside the integral. You get it? Okay, so our back to integral over C1 of f dot dr now will look like, let's dot it. So this thingy dotted with that thingy. You know what I'm saying? So this is 4 already and dot with that thingy. So we'll have negative 8, right? And sine cubed t. And in a dot product, we just add it up. So dot this thingy with that thingy. So we have 4, 8, 24. Good. And then cosine squared. And then sine t dt. And our t will vary from 0 to pi. How about that? With me? Can you handle this? Okay. Now let's go down, and now all we have to do is evaluate it. Okay. U-Substitution, right? Let me write it this way. From 0 to pi of negative 8 sine squared. Let's simplify. Let's not do that. What happens if I factor out sine squared? Yeah, I'll just write it. Then I will maybe erase it. Sine squared t plus 24 cosine squared t and then sine t. I regret not simplifying this thingy outside of the integral, right? Do as I say, not as I do. Always simplify your integrand first, then shove it in, and I shoved it in, and now I'm doing this. Do you see that some of them, actually, you can borrow 8 of these and then make it negative 8? Okay, fine. Convert this into 1 minus cosine square. Right? So do you see this? You have 32 of cosine square, and then minus 8. Do you see that? If you substitute 1 minus cosine square, so we have negative 8, and then we have positive 8 cosine square that gets added to this one. Very good? And this is u du, so we can just do this without making a substitution, right? Tell me you can do that. So negative, we pick up negative sign u du, negative. So this will be, this thing becomes cubed, right? Cosine cubed t, therefore divide this by 3, not to forget the negative sign, like that, plus, and this thing becomes just 8u cosine t, and from 0 to pi. U. And then, difficult part, right? Do that in my head, and I think, is that 16 over 3? Which I just copied from the answer key. Are you with me? Okay, that's just one of the paths. You, right? Okay, I'll do C2 and C3 here. Okay, I'm gonna do that with black color. Okay, at C2. Okay, my R, is it just T, I vector, this way, right? Plus 0, J vector. And then my T can vary from -2 to -1. Or you can have this thing from like -2 plus T, and then have T vary from 0 to 1. Whatever, right? But it really doesn't matter. Do you know why it doesn't matter? Let's take a look at our f. This is f of xy, except y is equal to 0 now, isn't it? So our f becomes this. Say yes. And let's look at what f is. F is up here. Oh, it has a y in it, both. So this thing just becomes a 0 vector now, doesn't it? Oh, we're done. That integral will give us 0, so we don't have to do anything, right? Wait a minute, is that also true in C4? Yeah, your f is still this. Good. So for both of this, your line integral C2 f dot dr, as well as your C4 f dot dr is equal to 0. Oh, thank God. There's no vector field at these two boundary, right here and right here. Because both of the vector field has the expression y in it, and y is equal to 0 right there. You with me? Okay, now we only have C3 left. Let's do C3 here. So C3, we have to come up with a vector function R, and that is, now we have to reverse the direction now, don't we, right? We're going that way, correct? So we want to start from -1 that way. So I say we put negative cosine t, I vector, plus sine t j vector like that, and have t vary from 0 to pi. Divide it, because when t is equal to 0, you have x coordinate -1, y coordinate 0, and then you get it. You want me to explain it further, or do you agree with this? Do you feel it? Okay, now we have to figure out f, right? Okay, f. Our f at x, t, y, t. Okay, Let's go back and take a look at f. F looks like this: y squared 3xy. Try to remember that. So y squared, this thing squared, right? So we have sine squared t I vector plus 3xy, right? 3 times this times that. So this changes back to minus 3 cosine t sine t. Are we good? Okay. I forgot to take dr, so I'm going to shove this thing down. Change that to red. Okay, let's take dr here. Dr is the derivative of this, so it becomes now positive cosine t I vector, right? Okay, plus positive cosine t though, sine t derivative, and cosine t j vector dt. Good. Now let's dot them. I'm gonna dot it here. I'm not going to make the same mistake twice, so let's dot it here. So we figured out f dot dr. We can pretty much recycle the previous one, but hey, just to demonstrate the correct way of doing it. So I'm dotting these two, so I will have sine cube t plus, or minus now, 3 cosine squared t sine ta. And then times dt. Say yes. Okay, wait, I'm gonna simplify it the same way that I did before then, eh? Yeah, might as well, we are in simplifying mode. So we'll factor out sine t, so we have sine squared t minus 3 cosine squared t, and then sine t like that, eh? Yeah, this is a better way of integrating. You simplify everything to death. And convert this to 1 minus cosine t. So you'll have, this is 1 minus, this is cosine t, and then you have 3 cosine squared t, 3 cosine squared t. So we have 4 cosine squared t sine t dt, eh? You with me? Okay, now we shove it in. Let's change the color to black. So here, integral over C3 f dot dr will become integral of from 0 to pi of that thingy that we simplified. So we have 1 minus 4 cosine squared t and sine t dt. With me? Say yes. Okay, this thing becomes then t. But what am I doing? Cosine t, because u is cosine t, right? So we sine t, negative sign, so this thing becomes cosine t, u, and then plus 4/3 u cube. So we have 4/3 cosine cube t. You with me? Because of the negative sign on du, this negative turned into positive. You with me? And since this is too much algebra, if I do it in my head, it turns into this. Okay, so what is entire line integral? That's annoying. What is the entire line integral? Therefore, I can say all of C of f dot dr, oh, circle, that's ugly. Hold on. F dot dr now, and all of C is equal to our previous value, what is it, 16/3 minus 2 over 3. So that's 14 over 3. How's that? Can you handle this? Yikes. We'll compare that procedure with Green's theorem. So we're going to convert this into double integral now, okay? Okay, so let me get a copy of my function f somewhere. Where is it? There, there's my f. I'm gonna copy this and take a cross product. Name of that thing is called the curl, okay? So here's my vector function. So you can see what's going on, okay? So if I take this thingy, okay, let's do this. So we have I vector, j vector, k vector, and then partial with respect to x, partial with respect to y, partial with respect to z of this thingy. So we have y squared, 3xy, and 0. Good. Okay, let's see what we get. So I vector, this is 0, and that's 0. J vector, that's 0, and this is 0 because this is z and we don't have any z. So k vector is the only thing that survives this. When we get to Stokes theorem, these ij terms all survive. It's not always 0, but this is a two-dimensional version. That's why we only have the k vector left. And that thingy is this part, which is 3y. And so I'm going to write it down. 3y minus, and this part, that's 2y, isn't it? K vector, which is just y. K vector. Say yes. Okay. So moving on. So I'm gonna say the line integral over C of f dot dr, that entire ugly thingy that we did before, were converted into double integral over d of this thingy, curl of f dotted with dA. dA, of course, vector is just pointing upwards, so to dotted with that k vector. You know what I'm saying? And that thingy will just turn into y dA. How about that? That's not too bad, eh? Yeah, but this is an ugly region, isn't it? Any suggestion? How are you going to do double integral over that kind of region?
Polar.
Of course we go polar. So let's go polar. So your r will vary from 1 to 2, eh? Radius 1 to radius 2. And your pi will vary from 0 to pi, eh? You with me? And your y, of course, is your r sine theta. And dA was r, another r, you get it? dr d theta. You with me? This is still infinitely easier because this is just one integral, isn't it? Okay, now 0 to pi of, now this is r cubed over 3, 1/3 r cubed. Evaluate that from 1 to 2. And then we still have sine theta. You want me to evaluate both integral at the same time because they're kind of independent of each other? You like that idea better? This is what I mean. If we just evaluate it, I'm going to shove this thing to the side a little bit. And we can this will give us a number. We can take it outside the integral and we do the sine theta, which becomes negative cosine theta, right? And then, I mean, this is just as good, saving time, right? And this miraculously gives you 14/3, which is exactly the same answer. Do you see why Green's theorem is a big deal compared to all this ugly work? Right? See, when you take a derivative, this is a form of a derivative, your integrand tends to get much, much simpler. And double integral is still easier than line integral in most cases. You get it? Okay. Okay, then I want to talk about this little weird thing, because most students get a kick out of this every year. Say we have the weird region. Say we have, and then we have this kind of, ooh, let's put it at the center at least, shall we? I mean, it doesn't need to be at the center, but say we have this kind of region. This is our D, this much, not here. There's a hole. How the heck are we going to evaluate this? Right? So suppose we want to do this double integral over D, D being this inside, not here. Maybe I should, let's see if I can. I'm being extra careful to not to mess up. This is D. You know what I'm saying? I'm almost there. That's my D. You get it? Okay. And let's curl across F. That is still pain in the butt. We can go polar and whatever, right? But I want to get something. How do you convert this into Green's theorem? Okay. So here's my proposal. I'm gonna cut this boundary. This way, right? So we want to go this way, and this way, and back it, which is exactly the same thing as our integral, our example. You know what I'm saying? So I'm going to call this C1, and this is C2, and this is C3, and this is C4. Exactly same way. So far so good. And then the other part, I'm going to have this thingy. This thingy. You know what I'm saying? So I will also go counterclockwise. So I'm going to call this C5, and this is C6, and going the other direction, and this direction, which is C7, and this direction, which is C8. How do you like it? And of course, this is then D1, and this is, the other side is D2. So I'm cutting this region into two separate, D1 and D2. And I'm going to deal with this separately. So this integrals do add, right? So over D1 of your curl of F dot dA. I forgot the dot in this previous thing. Let me put the dot back in. This computer doesn't want to erase. Dot dA, okay? So far, so good. Okay, then I'm going to add the red integral, d2. And then curl of f, curl of f, cross f, and then dot dA. Good. Integrals do add, they got 2. Now I'm going to use Green's theorem to expand this thing, okay? And I'm going to write these different line integrals separately. So this thingy is equal to over C1 f dot dr plus over C2 f dot dr over C3 f dot dr plus C4 of f dot dr, right? So which is just this upper, boom, 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 boom. Exactly how we did it in our first example. Second example. Now, likewise, I can cut these guys out, right? Okay, so then it's plus the red integral. Okay, let's start with C5. This one, C5 f dot dr plus C6 f dot dr, and you're probably wondering where is this thing going, right? C7 f dot dr, and lastly C8 f dot dr. Are you with me? Now I want you to take a look at these two integrals, okay? C2 and, oh shoot. I want you to take a look at C2 and C8, this integral and that integral. They are exactly the same integrand, and one is going to the right and the other going to the left in line integral. So they cancel, this thingy will cancel this thingy. With it. And then I'm going to use different, do I have different color? That's black, that's okay. And then likewise, C4 and C6 are same integrand going opposite direction. So they will cancel, won't they? Okay. Say yes. So what do you have left? Well, I got this thingy, which was C1. So I have C1 of f dot dr. Okay. And then I'm going to put the C5 back plus C5. Do you know why I'm putting it in this order? Let's just take a look at those two first. C1 plus C5, that gives you that outer circle, doesn't it? And then I'm gonna put the inside thingies, so plus, what do I have left? C3. It didn't change the color in time. This computer is really annoying me. Whenever I'm trying to color coordinate, this thing does not want to cooperate with me. Okay, C3 of f dot dr. Change the color. Let's see if it changed. No, it didn't. Did it change the color now? Yep, it did. This computer is really lagging. And C7 of f dot dr. Good. And I'm going to change color first, then talk. I'll change to black color, then talk. So these two gives you that this entire circular path, and those two, C3 this way, right? Clockwise direction. So they have two opposite directions. So what I have now is, this thing is C, what should I call it? Outside? See outside. That looks like count. I need a good notation, suggestion. I will take suggestions. That integral. And this integral, I'm going to put arrow that way to denote this is counterclockwise direction. What should we call this outside and inside thingies? We need a new name now. Should I just stick with out and in? Kobe, you're trying to give me a suggestion, but you are muted. Okay, out and in, uninteresting. See, out and see, in. How's that? Outside circle and inside circle. You with me? However, I want to reverse the direction of this thing, so they are both positive direction. I'm going to copy this, and I'm going to paste it here. What happens if I reverse the rotation? And just put it in the same direction. If you reverse the line integral, it becomes the opposite now, doesn't it? It's kind of like integral A to B versus integral B to A. You know what I'm saying? Plumbing professor concept. So this thing becomes this now. Why did I go through all that trouble? Okay, let's zoom out and look at the big picture now. I started with this integral, right? Which has a hole in it, right? So we can think of this integral as the entire circle minus the hole. Let's see. This is entire line integral outside, and then minus the inside thing. Is that very logical and expected? The whole thing minus the whole. Whole thing minus the whole. You get it? So this thing does exactly what you want it to. They got to, right? And then here's the kind of justification. We can cut it and then put a, because this is nice boundary. This is not a nice region, you know, if there's a hole in it. But you can still cut it and make it into nice region and patch it together later. That was the whole point of this.